Hey everyone, in this lesson, we're going to talk about climate. So, what exactly is climate? It's the long-term trends in precipitation, temperature, and weather for a particular location. So, when we think about climate, a really good way to understand what it is would be climate tells you what types of clothes you have in your closet. So, if we think about the Northeast region of the United States and the types of clothes that we would have in our closet for this climate, you would have cold weather clothes, warm weather clothes. You would have things to protect you during snow, and also pieces of clothing to keep you dry because of all the rain that we get. If you were to go to another region of the United States that has a totally different climate, like the Southwest region, you wouldn't need a lot of those types of clothes. You would just need warm weather clothes like shorts and t-shirts, and you wouldn't need any of that winter gear or any rain gear as well. Now, weather tells you what to wear each day. So weather is going to be those daily changes in the atmosphere. And what you wear due to the weather changes every single day. You might need a rain jacket one day and then shorts and a t-shirt the next day. So climate is long-term trends, weather are daily changes. So there are 6 factors that determine the climate. The first factor is different albedos, and you learned about albedo in one of the previous lessons. So just as a refresher, albedo is the Earth's surface ability to reflect the sunlight and therefore keep that area cool. So the poles are covered with ice and snow, which reflect back most of the heat, and that keeps them cold. But there's other regions of the United States that have a very low albedo, meaning that they absorb a lot of the sunlight and warm up as a result. This picture here is meant to show you the albedo values for different parts of the Earth. So if you can look up north here, Greenland is this large landmass, and that has, you can see it's mostly red, and therefore it has a very high surface albedo. So what that means, because it's mostly covered by snow and ice, it reflects a lot of the sun's light, heat, back outward into space and keeps that area cool. And then areas that have a bluer color, like all here in the United States and the rainforest region of South America and all around here, those areas, they have a much lower albedo, and therefore they absorb a lot of the sun's heat on the surface. All right, other factors why the temperature varies throughout the planet. The second factor is latitude. And because of latitude, it's going to be hottest on the equator, and that's due to more direct sunlight. So the further you move away from the equator, the further north or the further south you go from the equator, the cooler the temperature is going to be. And if you're along the north or the south poles, which are the furthest from the equator, it's going to be very, very cold. And that's because at the equator, the sun's rays concentrate on a very small area. And it's a much shorter distance, it's much more direct. However, when you are further away from the equator and you move north or south in latitude, the sun's rays hit the earth at a greater angle, and they have a longer distance, and they cover a larger area, and therefore they can heat up, or they don't heat up that area as much. All right, the third factor is topography and elevation. So it's going to be much colder at higher elevations, and this is due to less moisture and air molecules to absorb heat. So when we talked about the atmosphere in a previous lesson, we learned that the higher up you go in elevation, the less gas molecules there are. And the less molecules there are, the less heat that is absorbed, and also those gas molecules can hold moisture, so the less gas molecules there are, the less moisture that can be held in the atmosphere, and that keeps it cooler. So a great example of this is the Rocky Mountains, and a nickname for the Rocky Mountains is the Never Summer Range. And so if you look at this picture, it's taken during the summertime. However, in the front of the picture, or the foreground, it looks really nice, warm, and summery. But if you look at the background of the picture and you pay close attention to these mountaintops, you can see that they are coated in snow, and that's because those areas of high latitude or high topography and elevation are much, much colder, and therefore that snow melt is unable to melt because those temperatures are so cold up there. So to sum all that up, the higher in elevation or topography, the colder it's going to be. And that's because of the lower amount of heat and moisture that's held in those higher regions of the atmosphere. Okay, the next factor is the rain shadow effect. So what happens is areas that are coastal, and let's focus on the Indian area. So think of India and the Himalayas. That's what we're going to focus on. So what happens is you have moist ocean air moving off of the Indian Ocean, which is a warmer ocean. So that moist air that's very warm moves off of the ocean and travels over India. And it keeps India very hot. And even the area around India, like Bangladesh, it keeps it very tropical. And so what happens is as that air moves over the landmass of India, it pushes up the mountains, or the Himalaya mountains, I should say. So that air is forced up the mountains, and what happens is as it's forced up, it releases its moisture as rain or snow. So when it travels up the Himalayas, it releases it as snow, and before that, it'll release it as rain. Then what happens is as the air travels over the mountain, it becomes much drier because all that air has cooled and condensed right before it travels over the mountain range. So on the other side of the mountain range, that air has cooled and it has condensed and it becomes very, very dry. And that's why on the other side of the Himalayas, you have a desert, which is the Gobi Desert. So on one side, you have these hot tropical regions, pushes up over the Himalayas, and on the other side, because the air has dried out so much and condensed, you end up with a desert. The fourth factor is seasonal changes. And seasonal changes are due to the tilt of the Earth's axis. The number of daylight hours change in the northern and southern hemisphere throughout the year. So we talked about this earlier in the year, that the Earth revolves around the sun, and one full revolution takes 365.25 days. And so the reason that the Earth has seasons is because of its tilt. So depending on where you live in latitude will tell you whether you are tilted towards or away from the sun, and then that will also tell you what season you are experiencing. So let's look over here on this picture of the Earth as it's continuing its trajectory around the sun. And if we focus on the northern hemisphere, specifically the Tropic of Cancer. So this date is June 21st, and that's the summer solstice. So the Earth is tilted towards the sun, and the sun's rays are directly overhead or making a 90-degree angle with the Tropic of Cancer. So they are concentrating their sunlight on this area, which results in it to heat up and be summer. And then as the Earth continues its trajectory around the sun, we get over here to December 21st, which is the winter solstice, and you can see that the northern hemisphere is tilted. This is the Earth's axis, and it's tilted away from the sun. And therefore, the sun's rays have a longer distance to reach the northern hemisphere, and also the angle is greater there is less of a concentration of direct sunlight, and it's going to be much cooler up here. It's going to be winter in the northern hemisphere. Now, if you look down here at the southern hemisphere, even though it's called the winter solstice, down here, focusing on the Tropic of Capricorn, it's the first day of summer. The sun is directly overhead the Tropic of Capricorn, making a 90-degree angle and focusing its sunlight in that region, and therefore it's going to be much, much warmer. All right, so the next factor is ocean circulation patterns. And the water absorbs heat well and holds it longer than land, giving it a more stable temperature than land. Therefore, areas around water have more moderate temperature ranges. So we actually talked about this earlier in the year too, how the Earth has this natural conveyor belt of currents and a circulation pattern. And that's called thermohaline circulation.
Ocean circulation plays a key role in distributing solar energy and maintaining climate by moving heat from Earth's equator to the poles. At the ocean surface, currents are primarily driven by winds. Deep below the surface, however, currents are controlled by water density, which depends on the temperature and salinity of the water. In a few important regions, such as the North Atlantic, seawater can get cold and salty enough to sink to great depth. This globally interconnected process of overturning circulation occurs in all ocean basins and helps to regulate Earth's climate. Aquarius will measure the salinity in the ocean, giving scientists the tools needed to improve predictions of future climate trends and events like El Niño. Until now, researchers did not have a full set of data on ocean salinity and how it impacts climate change. Aquarius salinity data, combined with data from other sensors that measure sea level, rainfall, temperature, ocean color, and winds, will give us a much clearer picture of how the ocean works. Will higher temperatures intensify evaporation and alter sea surface salinity patterns? Will changes in salinity affect ocean circulation and how heat is distributed over the globe? Aquarius's measurements will provide a new perspective on the ocean, how it is linked to climate, and how it will respond to climate change.
If you look here at this picture, you can see all different currents and circulation patterns around the Earth, and there's one current that's probably the most familiar to you, and that would be the Gulf Stream right here. So, and we're really fortunate to have the Gulf Stream. It does a lot with climate regulation in this whole area, but also it's responsible for very warm water off the coast of North America or United States, right here around the Jersey Shore and even like Connecticut. That's what is responsible for those really warm ocean water in the July and August and even September months. So that current pushes off around here in the Atlantic and then pushes it up this region around the Florida Panhandle and then shoots it up this way, okay, all the way up towards the North Atlantic, along the coast and up the North Atlantic. Now, something else that you would notice is that if you traveled across the pond and you went to an area in Europe that's at the same latitude as New Jersey and New York and Connecticut, the water in these regions in the summer would be much colder. And that's because they're not fortunate enough to have the Gulf Stream warming up their water, so it would be much, much chillier there. And this is also the reason that hurricanes have the trajectory that they typically do when they travel across the Atlantic Ocean and then up the coast. So a really cool factor that has to do with ocean currents and changes and pressure systems is El Nino, and you might have heard about it before. El Nino is a condition where waters near the equator in the Pacific Ocean are warmer than normal. So they're seasonably warmer, and this happens every 2 to 7 years. And so winds that normally move the warm air are weaker, keeping the warmer air in place. And this results in more rainfall in the southern United States and equatorial South America, and also a drought occurring in Indonesia and Australia.
A natural force of nature unlike any other. El Nino is capable of unleashing a fury of climate changes and natural disasters that span from Alaska all the way to South America and beyond. What causes El Nino, and how are we affected by it? El Nino is not a storm, but rather a weather phenomenon in the Pacific Ocean. During an El Nino, the surface water temperature warms up, leading to complex weather patterns. South American fishermen in the 19th century, describing warmer waters during Christmas time, coined the name El Niño, Spanish for the Blessed Child. Nowadays, when sea surface temperatures in the equatorial Pacific Ocean rise 0.5 degrees Celsius over their historic average for 3 consecutive months, and once atmospheric conditions and rainfall patterns shift accordingly, scientists officially declare an El Niño. An El Nino event takes place about every 2 to 7 years. Normal east to west trade winds over the Pacific weaken, and warm water that normally travels westward is now moving toward the east. Moisture then rises into the air, and the effects of El Nino are felt throughout the Americas. In the ocean, warm water pushes colder water downward, blocking the important upwelling of nutrient-rich waters from the bottom. This causes some marine life to migrate to colder waters. Animals that normally feed on this sea life suffer, and fisheries throughout Central and South America suffer too. But El Nino's most noticeable repercussions are felt on land. In the western United States and Central and South America, the warm air and moisture lead to increased storms, rainfall, floods, loss of life and property, and the increase of some vector-borne diseases like malaria, even in places where they don't normally occur. In Southeast Asia and Australia, the opposite takes place. These areas suffer from drought, wildfires, and colder ocean waters. In 1997 and 98, the world experienced the biggest El Nino in recorded history. Some estimates blame that El Nino for 2,100 deaths and $33 billion in damages. Mongolia saw temperatures reach 108 degrees Fahrenheit. There was record flooding in Peru. And the U.S. saw storms in the Gulf Coast, flash flooding from California to Mississippi, and tornadoes in Florida. Scientists are now better able to predict if and when an El Nino event will take place. This helps communities better prepare for the changes in weather patterns and better adapt to its repercussions.
All right, so hopefully that gave you a better understanding of El Nino, and now we're going to talk about La Nina. So La Nina is the opposite of El Nino, and that's a condition when the water in the eastern Pacific Ocean is cooler than normal. So you can see that the opposite is happening based on this picture if we compare it with the previous picture. And so here's a little description about that.
La Nina is the cold water phase of a large climate pattern called the El Niño Southern Oscillation, the most influential climate pattern used in seasonal forecasting. Seeing La Nina develop helps predict climate throughout the United States months into the future.
During La Nina, the ocean temperatures in the tropical Pacific will begin to cool about Fahrenheit below average. When that starts to happen, there's a cascade of impacts across the tropical Pacific. The expanded pool of cooler than normal water shifts the normal thunderstorm activity westward from the central Pacific toward Indonesia, where waters are warmer than average. Strong thunderstorm activity pumps heat and moisture into the upper atmosphere, disturbing global circulation patterns. The jet stream, which is a river of air moving from west to east, begins to pull back or retract toward Asia. Downstream of that, over the Pacific Ocean and North America, there are pronounced changes in the circulation. Over the Gulf of Alaska, there tends to be higher than average pressures, with lower than average pressures over the western part of North America. Downstream, over the southeast, there are often higher than average pressures. This type of influence from one region to another over large parts of the globe is referred to as a teleconnection. Americans are interested in La Nina because of impacts over the United States. In general, La Nina leads to more cold air outbreaks over the northern tier, while it tends to be warmer and drier than average across the southern tier. The Pacific Northwest and the Ohio-Tennessee Valley are often wetter than average. La Niñas can last longer than El Niño, in fact, out to 3 years.
During a La Nina, the influence of the ocean on the atmosphere is steady and changes slowly. That's why climatologists are able to make predictions months in advance. From NOAA's Climate Prediction Center, I'm Ned Gardner.
All right, so hopefully that gave you a better understanding of how La Niñas affect the overall global climate. So this picture here shows you the Gulf Stream, which I had talked about earlier, and you can see how this like sandy color here, this is North America, and this area here is the United States, and the colors here represent the temperatures of the water. And you can see how those temperatures change. However, this area here is much warmer than it would be because of the Gulf Stream. So what happens is the warm water that originates down here is pushed up the northern seaboard, and it travels very quickly, about 2 meters per second. And as it moves up the coast, it cools down, and it pushes all the way up to the northern Atlantic. And as it cools down, it becomes more dense, and therefore it sinks to the bottom of the ocean. So the warm water that is lower in salinity is along the surface, and then it cools down, sinks, becomes more dense, higher salinity, and then travels along the ocean floor. So that is how the Gulf Stream works. All right, the sixth factor is global air circulation or convection. And convection is when you have warm air that rises and then cool air that is much more dense and sinks. So kind of think of a lava lamp. The bubble at the very bottom of the lava lamp where the light bulb is, it heats it up, and therefore, because that wax bubble is heated up, it becomes less dense, and it rises up to the top of the lava lamp. When it gets to the top, it's the furthest away from that light bulb in there, and it cools down, and then it starts to sink again. That is a convection cell. And so the movement of air, specifically wind, due to different temperatures, create local and global wind patterns, creating different weather conditions. So you can see in this picture, this is a convection cell. The warm air is less dense, and therefore it rises up, and then it cools down and falls back to the earth. So then what exactly is wind? As cold air sinks, which is more dense, it compresses and warms. The warm air then rises and expands as it cools, and also warm air can hold more water vapor. So what happens is solar energy warms the ground, which warms the air above it, and then cooler, denser air sinks and pushes the warm air up, and the cold air increases pressure on the Earth's surface. Air moves from areas of high pressure to areas of low pressure, and that creates wind. So that's what you're seeing here. Cool air creates high pressure, and then it pushes up the warm air or the low pressure. So this is showing you that whole, what I just read to you, or what I just talked about. You can see the warm air rising and then the cool air sinking and pushing it up. The pressure changes and pushes it up.
It comes at you as a breeze, as a gust, as a gale, or in the scariest of situations, a hurricane or tornado at speeds up to 400 kilometers an hour. Moving air can be as delightful as it can be frightening. But how does wind happen? Here's a one-sentence answer. Wind is caused by air flowing from an area of high pressure to an area of low pressure. The long answer is that there are a bunch of variables that affect wind formation, speed, and direction, including the sun and the Earth's rotation. But let's back it up a bit. The air that's all around you, it's made up of nitrogen molecules, about 78%, oxygen molecules, about 21%, and water vapor, between 1 and 4%. When we talk about air pressure, we're talking about the amount of force that these molecules exert on a given area. When a mass of air warms, it rises and therefore exerts less pressure on the surface. And especially if that air is moist, that rising air can become unstable and create cloudy, rainy, even stormy conditions. That's why low pressure systems are often associated with bad weather. But that low you see on the weather map is only low in relation to the air around it. There's always a mass of cooler, drier air, usually coming in from a polar region, waiting to rush in, push that low out of the way, and sit right on top of the land. That's a high pressure system, and when it dominates, clear skies usually come with it. So think of the wind as the atmosphere's eternally futile struggle to find a balance between these two competing systems. Air flows from a high pressure to low pressure systems to try to reach equilibrium, and in doing so, creates wind. The closer the high and low pressure areas are to each other, the stronger the wind. Now, unsurprisingly, the sun plays a big part in all of this, as it heats the surface of the Earth. About 2% of all the sun's energy that reaches our planet is eventually converted into wind energy, a small portion which we humans tried to harness. The spin of our planet also plays an important role. If the Earth didn't rotate, global winds would pretty much blow in straight lines with cold air flowing from the poles, heating up at the equator and then going back again. But the Earth's rotation produces a force on everything that's moving relative to the Earth, including air masses, a phenomenon known as the Coriolis effect. That rotation deflects the direction of the winds, to the right in the northern hemisphere and to the left in the southern hemisphere. Put it together, and these forces can do amazing things. According to most sources, the highest surface wind speed ever recorded was at the top of Mount Washington in New Hampshire. Wind gusts during a particularly brutal storm in 1934 topped out at 372 kilometers per hour. But in 1996, instruments about 10 meters above the surface recorded winds of 408 kilometers per hour during Cyclone Olivia off the coast of Australia. If it's all the same to you, I'll just take my gentle fall breeze. Thank you very much. And thank you to all of
All right, so this picture here shows you the different wind patterns and also the wind cells. You can see here, these are the trade winds here and here, and those are due to the Earth rotating on its axis. So that is climate.